Today, we are very happy to have Beatrice. We overlapped quite a bit when she was PhDing and I was postdocing at Penn State. This happens to be a major part of the reason why I ended up working on the sitter space, because Maitia Bayashtakar, our lovely boss, was doing that with the students, and I thought it would be fun to join in, which never happened. After that, I became a sellout and a dirty mathematical physicist and went doing higher spin gravity and all sorts of non-realistic crap. Well, Beatrice remained faithful to general relativity and to the real world. And for that, she was rewarded with an enviably short CV. So she did one postdoc in perimeter, and now she's happily assistant professoring in Radboud, as if that is how life works and everything's just fine. So from snooping around her website, she does a lot of nice outreach. So this should be an excellent talk. It also seems that, in this age of diversity this, diversity that, she made a courageous step and graduated her first PhD students who are identical twins. So may we all learn from this example. Please.
Thank you, Yasha, for this wonderful introduction. Yeah, I don't think I'll be ever introduced like that again. Okay, so yes, I'll be talking about black holes and gravitational waves. So before I start, I want to say that, be clear about my goal for this talk. So I hope at the end of this talk, you be convinced about how cool black holes are, which they really are. Even if it's just, already 100-year-old physics, they're really pretty awesome things out there. How awesome gravitational waves are and how we have this new field of gravitational waves astronomy. And I would like to see if we can collaborate. So that is, of course, somewhat of a hard pitch because I know probably most of you are not working on black holes. So I thought to make the link to maybe what you're doing a little bit more explicit by highlighting the tools that we have. So you see on some of my slides, there will be in the corners some boxes with some mathematical tools that I'm using to analyze these problems. So if you recognize something that you use or that you want to learn, we can see if I can be useful to you, or maybe you can be useful to me. Anyhow, so this is, if you see a box like that, I'm not going to talk about it, but it might ring a bell. Anyhow, yes. So I hope by the end of this talk, you will be that smiley face up there. Good. So let's see. What is a black hole? This obviously is not a black hole, right? This is our Earth. Our Earth has, if we were to measure it, has a circumference or a radius of about 6,000 kilometers. What would we have to do to create a black hole from, using our Earth? It's a little bit non-trivial. In principle, yeah, it can be done. You have to squeeze it. You have to squeeze it a lot. Everything on this Earth, like including you, this room, OIST, whatever, you have to squeeze everything to a ball with a radius of about a little bit less than a centimeter. Then you have created out of the Earth a black hole. So black holes are extreme gravity, right? There's a lot of matter in a very small region. It's a pretty wild object. So that is also the reason why we say that from out of black holes, nothing can escape, not even light. So the reason why we say not even light, because light is the fastest thing that can propagate in our universe. And I like this picture. This is sort of analogy. Of course, it doesn't all, not everything is the same as a waterfall, but you can think of a black hole or the radius of the black hole as being this part of the waterfall, right? So if you are, say, a fish or like us, right? We're away from the black hole, you're a fish, up here, you can still swim upstream, right, and get out. Like there's no problem. You can get away from this waterfall. But if you're a fish and you pass this waterfall, there's no way to, escape from this area. Same with black holes. So if you are close to a black hole, it's fine. You can escape. You might need like a super powerful rocket and lots of energy, but you can escape. But once you're inside the black hole, there's no way for you to get out. Whether you're light or whatever, there's absolutely no. So that's the reason why we say nothing can escape from black holes. But it's not like, black holes really suck up everything that's nearby, because, once you have enough energy, you can always escape. Just like the fish up here. It might cost, a lot of effort of that fish, but you can escape. But once you're across it, you cannot. Good. So black holes are extreme gravity. And now, even my mom knows what a black hole is, right? Like we may even say, in colloquial language, well, let's not do that. We don't want to get sucked up in a black hole or things like that, right? People use black holes as if it's like super normal. They weren't that normal, right? So they were discovered in the first time, like in 1916 by Carl Schwarzschild. He discovered, a mathematical solution that described a non-rotating black hole. Actually, which is quite remarkable because it's only 1 year after the discovery of Einstein's equations that describe general relativity, the best theory that we have to describe gravity to date. So quite remarkable, but at the time, no one really thought of it as anything to do with reality. Right? Black holes were just mathematical solutions. It took quite a long time until Kerr discovered the rotating black hole, which is actually what we expect, our universe, the black holes in the universe, we expect actually all of them to have some kind of rotation. So in fact, actually, the Schwarzschild black hole is not really the physical one. All of them will have some form of rotation. And, I think this is a nice highlight of the fact that actually, even though it was easy to describe the black holes, within a year, the non-rotating case, the rotating case is significantly more complicated. But even then, people just thought of these things, again, as mathematical, nothing really to do with out there in a real universe. Until like the 70s, that's when things changed. And now, right, like my mom knows what a black hole is. So we've come a long way. They're very common. I think this is for many things. I think in physics that we think of like a super normal as having always been like that, right? The expansion of our universe. I cannot imagine thinking that people thought differently about that, but many of these things have only changed, since like a few decades. And I think this is also the reason why one of the key people working on black holes, which was Chandrasekhar, made this beautiful comment, which I think is very nice, right? He's one of the pioneers working on black holes. He knows a lot. He said like the most shattering experience in his entire scientific career had been the realization that the Kerr metric provides the absolute exact representation of an untold number of massive black holes that populate the universe. So it was amazing to him to see that such a beautiful, in some sense, simple thing, like a black hole, really describe things out there in our universe. And I think it is indeed pretty cool. And the reason why it's such a shattering experience is the following. While black holes are complicated mathematical objects, at the same time, they're also extremely simple. Because to describe them, we only need 3 numbers. We need to know their mass, their spin, which we denote by a letter A, so how fast it rotates, and its electric charge. Now, we don't think the black holes in our universe have electric charge, so in practice, you only need to tell me 2 numbers to describe what a black hole is. That's, I think, something to be amazed by, right? Because we only know of like macroscopic objects, right? The fundamental particles of our universe, like electrons and things like that. Those you need if just a few numbers to describe them. But even to describe this, this whatever object is, right? We need many more numbers, right? We need to say, oh, it's made of some wood, it has this shape, blah, blah, blah. You need lots and lots of input to even describe any kind of relatively simple macroscopic object. Not for black holes. 2 numbers, and there's everything, you know everything there's to know about a black hole. That, physicists give us a name. We give this a name, the fact that black holes are so simple. We call this the okay, this is not working. We call this the no-hair theorem. So this has nothing to do with biology in any sense. This is just the fact that black holes are so simple. So in some sense, right, we say black holes are bold, right? They don't really have any nice features. And again, just to hone down this point that this is really special. Now imagine, this is from a textbook from the 70s, so hence this like kind of cool or like, I don't know, old picture. But here you have a picture of a black hole, representation of a black hole. And imagine throwing in some like a chair or some flowers or an old television and whatever this object is, I still have not been able to figure out. But anyhow, you throw it all in there. A priori, you would say, okay, I need many, many numbers to describe, this flower, this chair, etc.
I think it's a joke. I think it's hair. It's a wig.
You think so? Oh, that would be quite funny. Thank you. You have resolved this puzzle for me that I've been having for a long time. Anyhow, you should be amazed, right? A priori, I have all these numbers to describe, but after the fact, once all these things have fallen into the black hole only has two numbers, right? The mass and the spin. So before I have all these this information, and afterwards I don't, in some sense, right? So black holes, it's really special that they have no hair. It's a remarkable property. Now, one thing I've said that maybe you didn't really or thought about very carefully, but I said, right, black holes, nothing can escape from them, not even light. So then it's a fair question, how do we even know they exist? If we cannot see them, right, because that's how we see things, that light, reflects on things and etc. That's how we know things exist. If we cannot see the light from inside the black hole, how do we know they exist? Well, multiple observational indications. One is the impact that black holes have on other objects. For instance, almost every galaxy in our universe we think has a supermassive black hole inside of it, including our own. So in our Milky Way, we can track the orbits of stars very well. And here you see some of those orbits. And the only way to explain sort of why the orbits take this particular form is to say, well, there has to be in the center a very massive object with about 4 million times more massive than the mass of our sun. And since it has to be within a very small radius, because otherwise it would collapse with all these objects, it will have to be a black hole. Another thing is that we cannot see light from inside the black hole, but we can see light from near the black hole, so close to the black hole. For instance, right, some black holes, not all, but some have accretion disks around them. And in these accretion disks, particles can flow around and they can also emit light. In fact, if you've ever seen this famous picture, this is a picture of the first picture of a black hole that has been created by the Event Horizon Telescope. This is a picture actually not of the black hole, but of the light coming from the accretion disk around the black hole. There are also other cases where you can see light from close to black holes, and that's, for instance, when a star is being sort of ripped apart and swallowed by a black hole. This goes by the name of the tidal disruption event, and we've also seen that. This is, of course, an artistic representation. It's not quite what you see in the data, but okay, good. And of course, the last thing, how do we know they exist? Well, with gravitational waves. So here you see the first gravitational wave that was ever directly detected. And this happened exactly 10 years ago, well, plus 3 days, that this event was seen here on Earth. So what do we see in this plot? Well, the top part is, here you see a wave. This is the gravitational wave that we've seen. And it is generated by 2 black holes going around each other. So that's this first part. And they get closer and closer. They collide, they merge. And then, this highly deformed black hole wants to become like sort of an ordinary simple black hole, right? That is just described by the mass and the spin. And it's sort of in this relaxation process, it will also emit some additional gravitational waves. This is a very cool event where you can see also everything is extreme about it, right? So two black holes, both, about 30 times more massive than the sun, that go at like incredible velocities, right? So here you see the velocity, they go up to about like almost 60% the speed of light at the time they merge. Can you imagine, right? Like these like very massive objects going at these tremendous speeds. I think it's pretty insane. It's also pretty remarkable if we look at this number up here, this strain, 10 to the power minus 21. Remember that? I'll come back to that. And I just want to show you how is this achieved? Well, we see this with gravitational wave detectors. And for that, we need multiple of these things. So here you see me as a PhD student being super happy that I got to just, go to one of these detectors because I'm a theoretical physicist. I never, or I typically stay clear of actual experiments, but, this is so cool. I had to go see one of these detectors. And this is the one in Louisiana where, so here in the center you have, well, the detector, this is the operation center, so to say, but the detector is essentially two extremely long, 4-kilometer long arms where light is being bounced around so we can measure distances very precisely. Everything is super cool about that experiment. In order to do this, those 4-kilometer arms, they need to be almost perfect vacuum, better than you find in, out in space. All kinds of like records are being broken. It's really remarkable that this can be done. Good. So as I said, this is extremely challenging, right? That's also the reason why it was only 10 years ago that it was done for the first time. So why is this extremely challenging? Well, on the experimental side, in order to detect the gravitational wave, it works very differently from detecting light, right? So light, you use a telescope, but in order to detect the gravitational wave, what you need to do is measure distances extremely precisely. How precisely? Well, that's that number of 10 to the power minus 21. That is the relative precision with which you need to measure distances. So just to give you some kind of feeling for that, that would be like measuring the distance to Proxima Centauri, the closest star to Earth, other than the sun, obviously, with a precision of 10 micrometer. That's pretty wild, right? That apparently we can do, or, my dear experimental friends. Also, that's one part of it. So experimentally, like I said, many remarkable things need to be done, but also on the data analysis side, it's actually not so trivial. So the signal, right, that we might be after would be like this light blue thing, but what you get is the dark blue stuff. So you need to be able to extract the signal, like the signal that you want, right, that you're after, is much less essentially than the noise. So for that, all kinds of cool tools are developed, which goes by name match filtering, and that also needs to be done. And because we need this match filtering, right, so we need to have extremely accurate models for what we might see in these detectors, right? Otherwise, we cannot use these match filtering techniques. We need extremely accurate description of, what kind of wave do you get if you have two black holes colliding. Now, since that first detection 10 years ago, there are about 200 events that we've seen. So here you see some part of the recent catalog where essentially all these curves up here, they're now not in the time domain, but in the time frequency domain. They look like this. These are almost all just describing two black holes colliding and merging. And in some cases, neutron stars with black holes or neutron stars with themselves. So lots has happened since. Now, what we've seen in all of these cases, though, is that all these black holes that we've seen, they have roughly similar masses. So they're in this range, the stellar black, we call them stellar black hole because they have masses somewhat similar to the mass of our sun. And just as a reminder, the mass of our sun is 2 million kilograms. I looked up this word. Million means 10 to the power 30. So it means a 2 with 30 zeros. Good. So we've seen black holes roughly with stellar masses. So, maybe 1 to 100 times the mass of our black hole. But in our universe, in principle, we have black holes with essentially any size. So there could be something that we call supermassive black holes. Those, are the ones that you saw, right? That the picture's taken of, the Event Horizon Telescope. The one in our Milky Way, in the center of our Milky Way, is a supermassive black hole. So those can be like 1 million or more massive, million times or more massive than the sun, or something in this range, what we call, not very imaginatively, the intermediate mass black holes, or even lighter ones, the primordial black holes. So here I have a question mark because the observational evidence for these is still not very strong, but I think that's just sort of an observational bias. This will happen soon. I can put some nice pictures here too. The primordial black holes, we don't know if they exist, but they might be, and they might explain part of the dark matter puzzle that we have in physics. Now, the reason why we have black holes in all sizes, in principle, in the universe, is also actually pretty remarkable. You should sort of be surprised by that we can have black holes in all sizes. Because any other object sort of that we know of, right, like humans are always roughly like 1 to 2 meters. We don't have humans that are a kilometer size, right? Everything in our universe here on Earth, but on Earth typically has a typical scale. But even for stars, this is true, right? So you may have stars that are about 100 times more massive than the sun, but you don't have a star that's 1 million times more massive than the sun. So why is that? So why can we? Well, the reason for that is that typically everything has, a natural scale associated to it. So we humans, right, typically things are made up of, say, atoms, right? And atoms have a scale associated to it. So there's like limited things that you can do with a given object. So for neutron stars, the neutron stars are mostly made up of things related to neutrons. So therefore you get a specific length scale, and therefore objects have a range that is allowed. But for black holes, this is different, right? Because black holes are vacuum solutions of general relativity, of gravity. So the only two relevant fundamental constants that go into play in these solutions are G, right, and C. So G is Newton's constant, C is the speed of light. With those two numbers in 4 dimensions, I cannot create a length scale. I would need H bar or something, so a quantum thing. But we're not talking about quantum stuff. So because of that, there's no length scale, and that means that the mass can have any value. I think that's pretty cool. Now, as I said, right, so far we've seen, black holes merging with this typical stellar mass size, but we have a whole gravitational wave spectrum. Okay, so currently we detect waves that are about 1 hertz, say, regime, with these terrestrial interferometers. So we have, I showed you the picture of LIGO where we just saw 1 detector, but in fact LIGO consists of 2 detectors. There's also a smaller detector, Virgo, in Europe. And now in Japan, we also have Kagra. So there's a whole detector network. So these terrestrial interferometers, since they are, the antenna is roughly 4 kilometers, more or less, they are sensitive to black holes in this particular stellar mass range. But, good. Just like light, right, is a wave, and you can have light of, the visible light or infrared light, etc. Similarly for gravitational waves, there's a whole spectrum. So soon-ish, as in mid-2030s, we also hope to have a detector up in space called LISA that would be sensitive to the millihertz regime. And currently, we are also using radio pulsars to detect gravitational waves as well in a much even smaller frequency area. Good. The cool thing about that is, right, you want to have these detectors at different skills, right? Because you would also be sensitive to different sources. Similarly, right, if you have you build your radio. If you have a bigger antenna, you might be sensitive to different frequencies than with a smaller antenna. The same happens here. With these terrestrial interferometers, right, we're sensitive to these stellar mass black holes, but with LISA, we're going to be sensitive to supermassive black holes merging, as well as extreme mass ratio and spirals, which I'll come back to, and other things in our universe, such as, maybe even gravitational waves from the early universe associated to the Big Bang and inflation, and many other cool things that I'm not going to talk about. So there's a whole zoo of gravitational wave sources that we're still going to see. So what can we do? Well, we can see just these black holes merging, but why would that be interesting? Well, there's lots of stuff you can do with them. What happened there? Yes. Well, if you see these black holes merging, what can you learn? Well, you can learn about the formation and evolution of these compact black holes, and as well as stars, compact stars. You can learn about the structure of our Milky Way. You can trace the origins, growth, and history of these massive black holes as you detect many more of them. You can even do things like cosmology. You can measure the expansion rate, so the Hubble expansion, which is currently, if you followed any of the cosmology, we have different measurements from different epochs in our universe, and they all give you a different Hubble rate. So it would be great to have sort of an independent measure of the Hubble rate, which could be done with gravitational waves. Similarly, you might be able to measure dark matter around massive black holes with gravitational waves. If you see them from the early universe, we don't know if they're there, but if they're there from our universe, that could also have very cool implications for particle physics. And I don't know, who knows? We might see gravitational waves from things we haven't even thought of, right? Like our universe always keeps on surprising us. So maybe there are even other weirder objects than black holes out there. Similarly, you can also not just stick to astrophysics and cosmology, but do fundamental physics with gravitational waves. Right? Our universe essentially is a beautiful lab, and not everything needs to be on our tabletop experiment, right? We could just look up, and amazing things are created. So, for instance, right, we can see gravitational waves from the merger of neutron stars. If you look inside a neutron star, the densities in the neutron star are way higher than anything we create here on Earth. So if you can probe that information with gravitational waves, which we can, you can learn about matter at extreme densities, right, the nuclear density. Similarly, you could test general relativity, right, because you are really probing a very strong field regime. You can test the nature of black holes, and possibly, then this of course depends on what's out there, discover new particles. So, one of the challenges is for the standard model physics or beyond standard model physics are that, there might be many other particles out there, for instance, axions and things like that, and they would or could naturally form clouds around black holes and things like that. This is something that you could also see with these gravitational wave detectors. So I think there's lots of amazing things that we can do with these gravitational wave measurements. So how am I related to this? Well, I like to explore just anything that I can, as long as it has to do with gravitational waves and black holes. And not necessarily black holes, but black holes are one of my favorite objects out of all these things there. So this is just a sort of a wild picture just for people to see or maybe relate to any of these things and ask questions about them. But I'll not talk about all of them. I'm going to focus on just two pieces of them. And then, good, we're doing, and explore them a bit more. I also wanted to mention, I have a small side business. Most of the time I stick to just general relativity and real world physics, but some of the time, well, I think QFT on curved space-time is also real world physics. But anyhow, I have like a small side business in that. I just wanted to mention that. So if you're interested in that, I'm happy to talk to you about entanglement entropy as well. Good. Anyhow, back to the black holes and gravitational waves. So here, right, we've seen this before. This is like a typical gravitational wave from a black hole. You may get the wrong impression by now that most black hole waveforms look very simple like this, that's actually not the case. It would only be for sort of like a vanilla scenario where you have two non-rotating black holes, merging in the equatorial plane, all this. And just to say, right, most gravitational wave signals are actually way more complicated than that. But the vanilla type will look like this. And as physicists, what we do to model this, we quantify these different regimes. So we pull when the two black holes are still far away, the in spiral. And then when they get very close, the merger. And then we have this ring down phase, the relaxation phase to become like a normal single black hole again. And these phases, the transition is not hard cut, but they're sort of determined by how we describe these things. So we have different approximation techniques for each of these phases. So when the two black holes are very far away, we use something that we call post-Newtonian methods. When they are about to merge, we don't really have any approximation methods. So the only way that we can solve that properly is to use full numerical simulations. And then this final phase, again, we can describe very well with something that we call black hole perturbation theory. Now that final phase, I think, is very cool, right? And that's what I'm going to focus on for a bit. Because that final, yes.
Can I just interrupt?
Yeah, anytime.
This time axis
Yeah.
that you have going, you cannot observe it in real time, right? So you're watching multiple different black holes to determine when these different phases are.
No. So the cool thing is
You can actually observe it in your lifetime,
Yes.
a whole thing going.
Yes, no,
What's
so
the time
basically-
axis?
Oh, yeah. No, this is the cool thing. This process is absurdly fast. So I did not really highlight that at all. But okay, in this here, this is like a fraction of a second.
Oh.
So admittedly, these black holes are already quite close when you see. So in principle, when the black holes are very far away, they also emit gravitational waves, but they're typically too weak. So they only, the gravitational wave signal gets stronger and stronger as the black holes get closer. So more and more energy sort of is being emitted. And that's what we see. So we only see, well, here you can't see, but like when they're roughly, if you want to measure things in the size of how big the black hole itself is, when they're, 8 times as away from each other compared to their own size. So so this is something we see, and it's shockingly short. It would be great. I mean, and we are getting better. The detectors are being improved, etc. There will be new detectors made, and we hope to see more and more of this earlier part, because that has also lots of rich information in it, which we currently don't have access to. Yeah. But you have to be, of course, lucky that black holes are merging when your detector is on, but our universe is very big. And there are lots and lots of black holes in our universe. So this is actually essentially happening all the time. So over these 10 years, we've seen about 200 of these events. But with the next generation of detectors, we might see 200 of these events in 1 week. So our universe is a big place with lots of amazing things happening all the time. Good. Anyhow, so back. By the way, indeed, if you have any questions in the meantime, please interrupt me. It's more fun. Good. So focusing on this final part, which is something that I study specifically as well, is called this ring down phase. This ring down phase is very cool because it's in some way very simple, right? I mean, if you're a physicist, you might look at this and say, hey, this looks like something I know. This is just some damped oscillations, right? These damped oscillations, they're easy to describe by something that we call quasi-normal modes. If you want an analogy, think of a bell. If I hit the bell, right, with, say, a hammer, I get some tones out. And then from the tones that I hear, I can actually determine some of the properties of the bell. So as you can imagine, right, bigger bells, you hear lower tones. Smaller bells, higher tones, things like that. So depending on how much information you get and all that, but you can in principle determine some of the properties of the bells. And it doesn't really matter if I hit the bell with say a hammer or with an arrow. Both times I get music out, of course, the amplitudes of the sound will be different, but the tones that you hear, they'll be very similar. Same with black holes. But black holes are in fact actually way simpler than this kind of bell, right? So to describe a bell like this, I need many parameters, right? I need to know the material, the shape, et cetera, et cetera. But for a black hole, I told you, they satisfy this no-hair theorem. So just 2 numbers. So if I hit a black hole and I listen to it, and I can determine which frequencies are in that signal, I can determine the mass and the spin. So that is actually how this is done as well. So because the sounds of a black hole are damped, we can decompose our frequency into a real part, which is the actual frequency, and an imaginary part, which we call the damping time. If you're not familiar with complex numbers, don't worry. They're essentially 2 numbers that we can extract from the frequency. So the damping time. Now, right, as I said, with these, if I can analyze this signal, then I can determine, if I measure these frequencies and damping times, how big, or equivalently, how heavy the black hole is, because these things are directly related, how fast it rotates. And I can do something that's very cool. I can check consistency with general relativity. How does that work? Well, right, if I measure one frequency in this signal, I get 2 numbers out, right? I get the real part and the imaginary part. So I can determine the mass and the spin already. If I see an additional frequency, I can also determine the mass and the spin. So better be that from those 2 measurements, the masses and the spins agree. They do not, right? It's not a black hole. So this is a very non-trivial consistency check. Again, for the analogy, right? If you, by listening at the tones, right, you can probably even, we as non-experts, right, we can listen to some music and hear whether that's a cello or a violin, right? Similarly, if you're like, use your fancy data analysis tools, we can determine, right, how big and then small the mass of the black hole is. And this all goes by the name of black hole spectroscopy. And I think it's a pretty exciting field. And in fact, well, these are the tools that we're using for that. You may be surprised that you see something that the time-independent Schrödinger equation, while I'm doing classical GR, it's sort of miraculous, but if you end up doing black hole perturbation theory, you end up with an equation that just looks like the time-independent Schrödinger equation, but of course has nothing to do with quantum mechanics. And that's just a side note. Now, as of last week, you may have seen on CNN something, a headline like this. That was pretty cool because last week, the analysis of this new signal was revealed. All these gravitational wave signals, they get not very exciting names. They are all called GW for gravitational wave. And then the year, month, and day. So everyone has, their favorite phone number, so to say, for some of these events. So this was an event from January this year. And in this event, they were actually, again, 2 black holes colliding with an amazing signal, very high signal to noise ratio, all of that. And they were indeed able to already detect 2 modes for the first time. And I think this is essentially, since as of last week, we can actually already do black hole spectroscopy. We can detect 2 modes. And this is what they did. And that is related to this, well, part of the statement that you saw in the CNN headline. Actually, if you asked anyone in the field whether they would have thought that this is possible with the current detectors, no one would have dared to say that this, or dreamt even that this would have been possible. People thought we had to wait until the next generation of telescopes, so we had to wait another 10 years, but we can apparently already do that. So I think this is very cool. It makes me very happy because, it's a highly non-trivial test. And in fact, right, with the next generation of detectors, we will not just detect 2 modes. The forecasts are that we are likely need at least 8 modes or so. So that means really, really stringent tests of general relativity and the nature of black holes. Yes.
What does it mean two modes? Is it, are you detecting the frequency of the two black holes before they fuse, or this is all after they fuse? I don't get it.
Oh yeah, no, great. So this is after they fuse. After they fuse, you get a wave, and the wave will, so you can have, most waves are more complicated. They're not just a single tone. Most waves are always multiple tones. And in this wave, what they were able to detect were two of these tones. Resolve it clearly. Even if you listen to music, right? Even if you plug there are multiple tones that you hear at the same time, and you can do some fancy math, like Fourier analysis and all that, and extract the different tones. So from this case, this was after the two black holes have merged. They were able to determine two of these tones out of that signal, which is, I mean, to me, fantastic. I mean, maybe not to you, but to me, that's really, really wonderful.
What does it mean? What does it mean, these two tones?
So these two tones, so yes, it's like, you know, if you...
What do they represent, the two tones?
Good. They represent the properties of like this black hole that is highly deformed, and it wants to become, you know, like a nice simple black hole. And it's just like, it wiggles away. It's like, you know, non-nice properties. So, those are the ways that you see. And those have an imprint of, you know, what the final mass and the final spin of the black hole are. So it knows about those things. Yeah, that's, I hope that answers your question. Good. So what's my work? Well, one of the things I'm trying to do is essentially make that model for that wiggling, that becoming like a normal better. So what I do is I include nonlinear effects. So I told you, right, we use black hole perturbation theory to describe that final part. And until like 3 years ago, everyone was just using linear black hole perturbation theory. But we actually discovered that that's not enough. We need to go to a higher order in perturbation theory. So if you never worked with perturbation theory, then these words don't mean anything, but for physicists, it will mean something. And I think this is really cool. So why? Let me just indulge in this. So here, I am plotting a typical map where you see here on the horizontal axis, the frequency, and here, well, the inverse of the damping time. So if you know the mass and the spin of a black hole, you can say, okay, this is a typical frequency you can have. That's another one, that's another one, that's another one, that's another one, but nothing here in between. There's no frequencies there. So, and if you were to have, like, say, a slightly different spin, then these dots would move a little bit in this plane. So that is one way to determine for you what the masses and spin are. So for that black hole from last week, these two frequencies were measured. But, you know, with the next generation, we might see also something like this, the star. Of course, the star is a little bit my bias because I like that. This is one that comes from second order in perturbation theory. The reason why I think that's cool is, well, once I think that's great because general relativity is inherently a nonlinear theory. So it'd be great if you see something that's nonlinear, but also typically, right, nature, right, as a theorist, I sort of set up my calculations. I love to do perturbation theory. It's great, it's easy. I say, okay, this is my linear part, this is my second order part, etc. But nature doesn't care on how I approximate it, right? Nature just gives me the full shabam, right? It tells me, here's, you know, what I am, right? Regardless of how you try to approximate me. But this is not the case for this frequency. This frequency is fingerprinted with which order in perturbation theory came from. So if you measure this frequency, you know it comes from second order. So that's, in that sense, is a very clean way to disentangle the linear and the nonlinear part. It sort of rarely happens that, you know, you actually have a measurement where you can disentangle these things so cleanly. So I think this is a very nice, and it would be very cool if we get to see that. And there are some forecasts already now that tell us that, you know, with LISA, one of these detectors in space, we actually will be seeing things like this. So I think that would be great. It will be a new kind of test of general relativity. So I'm excited about that. And that's also why I work on this. Another thing that I work on are extreme mass ratio inspirals. So what are they? Let me try. A fancy, well, hopefully fancy, relatively fancy animation made by one of my friends, Lorenzo. What you see here is a supermassive black hole in the center, and well, this fast guy going around it. So this is, well, I cannot even track it, it goes too quickly. There is another black hole going around it. So in the center, supermassive black hole, you know, say 10 to the 6 to 10 to the 8 solar masses with, you know, a typical small object of say 10 solar masses going around it. Hence this name, extreme mass ratio inspiral. This is a type of signal that will generate a wave like this, you know, has many more features, is much richer, etc. So why is this a cool system? Well, first I have to admit this EMRI, or for short, right, extreme mass ratio inspiral, we have not observed yet. Why have we not observed that yet? Well, for one, it's very hard to see with electromagnetic radiation because that small black hole is very close to that massive black hole. And, you know, since they're both black holes, right, we don't really see any light of them. There's no way for us to see it any other way than with gravitational waves. So we need gravitational waves, but this kind of system emits gravitational waves in the millihertz regime. And our current detectors just are not in that regime, right? They're in the Hertz regime. So that's why we haven't seen them. But we are going to see them, hopefully, with LISA, right? The one in space. And in fact, we're going to see them, not just, you know, the few orbits that I showed you for the current ones, but we're going to see them, you know, for like 10,000s of orbits. That's, you know, pretty amazing, right? Because now you can imagine, right, with these 10 wiggles, we can already do great science. Imagine what you can do if you can actually see like 10,000 of those wiggles, right? That means that you can do extremely precise tests of essentially what the central massive black hole is. And in particular, you can measure the mass with a relative precision of 10 to the power minus 5 and the spin with a relative precision of 10 to the power minus 4. Yes?
So naively thinking, if you have a supermassive black hole and a smaller black hole, I would think that many black holes would be doing this orbit at the same time. Like, or do we consider these?
Yeah, so in fact, actually, we expect, no, that there are not many of those. We don't know how often this happens, but the current estimates for the rates are roughly between, well, that we see either 1 or 1,000 of these events per year. So it doesn't happen so often. There are not that many black holes close to a supermassive black hole, according to current best astrophysical models of the environments of supermassive black holes.
Any short intuitive reason why?
It's not super intuitive, right? You need to make some population models. I'll try to think of an intuitive reason. Yeah, it's a good one. So yeah, we are going to see them. We can do extremely precise things. It's, you know, if you think about anything in astrophysics, right? If you can tell me the mass, you know, within a factor of 2, like people will clap and cheer for you, right? Like this is a great measurement. Here you can measure something with a precision of 10 to the power minus 5. That's for astrophysics, of course, wild and not necessary. But if you want to test things like general relativity and want to do fundamental tests of the nature of black holes, then this is great, right? So let's see. How am I doing on time? Oh, okay, good. So, however, MRIs, I think, are likely not isolated. And most of our models sort of assume that, you know, we have a massive black hole, small one, and vacuum. But it could be, right, that you have, say, another black hole out there. A little bit like the question you're asking. So what would this effect be? Well, you know, in fact, you can make some estimates. So if you look in the literature and you try to come up with some typical estimates, what you would find is that, say, you know, if you take these distances, this next one is already kind of far out, effectively. So you don't need to look at these numbers, but it's relatively far out. So then you can do some back of the envelope calculation. And that we learn, at least to do in physics, where you say, well, let me at least look at what's sort of the Newtonian tidal effect. Right? So let's not do some fancy general relativity correct calculation that we should be doing, but let's at least estimate with Newtonian things, because this black hole is already quite far out. Then you find that if you estimate what this number is, which is essentially the dimensions version of your tidal force, you get a ridiculously small number, like 10 to the power minus 13. So at this stage, you might be saying, well, you probably don't need to worry about that. And you're in fact actually right for most of the orbit. Because also, if you sort of think about it intuitively, this thing is sort of like a tide. So as this thing goes around, it averages out. Very much like the tides that the moon creates on Earth, right? So, at times we have a high tide, and at other times we have a low tide. And on average, we sort of have no tide, right? The effect averages out. But as it turns out, that's true for pretty much most of the orbit, but you can get things like resonances. So resonances happen when you have a matching of frequency. So if you ever watched Mythbusters, I think there's like one very cool episode, or at least I was amazed by this as a child, where they hire an opera singer or something to sing at a very specific frequency. And just by doing that, they managed to break the glass. Right? So there's no physical interaction between the singing and the person is just singing and the glass breaks. How is that possible? Right? Well, if you sing just at the wrong tone, nothing happens, right? So, but if you match the frequencies of, in the sound wave, so of your singing, to the natural frequencies of the glass, then you can get a very efficient transfer of energy from the ones in the sound waves to these mechanical vibrations, and boom, the whole glass shatters. Something similar can happen in black holes. So what are the relevant frequencies I'm talking about here? If I look at a black hole, it also has 3 frequencies. I need 3 frequencies to describe this orbit. As you can see, it's a complicated orbit. We need 3 frequencies. We call them the ones for the radial direction and the 2 angular directions. Far away, if you're far away from the black hole, those 3 frequencies are essentially all the same. If you're a physicist, that makes sense, right? Because you learn that the 2-body problem, you can go to the center of mass frame and you just need to describe it one frequency. So that makes sense. Far away, they're all the same. But if you're in the strong field regime close to the black hole, you really have 3 different ones. Now, if you get an interaction between these 3 frequencies of the black hole and that perturber that's really far out there, so I really only need 1 frequency to describe it, whenever that happens, I can get a resonance. And that can lead to, for instance, something like this. So here I have plotted a scenario where a resonance happens sort of early on in the in-spiral. At that time, right, it's a small effect. But since you see so many orbits later, you can easily tell just by eye that, the one with in green is the one without or with the resonance, and the one in red is the one without resonance, right? And other than that, the 2 cases are the same, right? You can tell by eye that they're different. So even though you have such an extremely small perturbation to your system, it changes the waveform dramatically. And this cool effect is something that we discovered and we called by the name of a tidal resonance. And I think, there are 2 perspectives one can take of this, right? But if we have data with a tidal resonance in it, right? If we do not correctly model this, we either, may be making bold claims like saying, hey, general relativity is not correct, right? Because it doesn't match with our predictions. Or, maybe be less wrong in the sense that we infer the wrong parameters of the system that we're trying to describe. Or maybe even miss the system altogether. So if you have multiple resonances, you might not be able to even extract it from your data because you need, right? As I said, we're using this technique of match filtering. So we need a very accurate model. If our model is not accurate enough, we cannot even sometimes extract the signal. On the other hand, that's sort of the pessimistic view. If we are correctly modeling this, then we can learn these valuable information of, what is the next black hole out there. So this is kind of a cool probe, right? We are probing a black hole indirectly with its influence on the gravitational waves by these other two black holes. So I think this is kind of a very neat way to even get more information of the environment of very massive black holes. So of course, the key part is we need to model this correctly, and that is one of the things that I'm working on. So of course, right, the first thing we did is like this very vanilla model where we make all kinds of simplifying assumptions, and now it's time to upgrade all of these things. So let me conclude. It's good. I'm doing well on time. I hope that, well, you now know that gravitational wave astronomy is only 10 years, well, plus 3 days old, and that lots of exciting physics and astrophysics are already being uncovered. This is only the beginning, and I hope you stay tuned. Thanks for listening, arigatou gozaimasu, and for having me here. And I will be at OIST until the end of December, up here at Lab 5. So please come see me, shoot me an email, or talk to me after. I would love to learn about what you work on and how we might help each other out. That's it. Thank you.
Thank you. Questions?
Thank you for an interesting talk. I would like to ask very basic question. So if two black holes that have different masses, different speeds, and different spins merge together, do you have a way how you can predict how the final black hole will look like? Will be the mass, speed, and orientation?
Yes, we have that, but it's the way we do this. The only way to do this is sort of the way we do this is we make actual models for give me a mass, a spin, etc., etc. Then we have to evolve the whole system and then see what the final result is. And we've just done that for many sort of configurations, and then we do some kind of fitting algorithm. So they're sort of like fits for this, but they're all sort of in some sense some black boxes, right? So the fits are not, are just fits. But they are somewhat predictive. But if you really want to know the actual answer, you have to evolve the entire system to know what comes out. There's no shortcut or something that tells you, well, if you take this, there's an actual formula for you to tell you what the final result is.
And another question, like usually when you fuse two physical objects together, a huge amount of energy is released. So does this also apply to the black holes, or that's the gravitational waves you were talking about?
Exactly. Yeah, you're right onto it. There's a tremendous amount of energy released in these gravitational wave mergers, and all of that is released in the form of gravitational waves. In fact, okay, so don't quote me on the numbers, but I think if you were to describe this in terms of power, I think, for instance, the first merger that I showed you, the first detection, the amount of power in that emitted in those final phases of the merger is of the same order as all the power of light in our visible universe. So wild forms of energy, right? Sort of equivalently, think about it, there's about, I know for that first merger, there was about 3 solar masses in gravitational wave energy released.
So does it have any destructive effect to the surrounding planets, galaxies, whatever?
So gravitational waves, so what they do, they stretch and squeeze things, so to say. But typically there's not, the effect is large sort of nearby, but typically there's not much else stuff around it. And it's propagates sort of, almost undisturbed through everything, almost. In that sense, it's much nicer than light. Like gravitational waves bend less, so to say, than light and things like that. So it's easier to track its origin, but it doesn't. Yeah, don't worry. Like it doesn't disturb anything much. I really need to do a lot of work, right, to actually see these things with a detector, right? So
Thank you.
But let's notice that your first 2 questions were the same question. because the fact that a lot of energy gets radiated is precisely why it's hard to calculate the final mass, why it's not just the sum of the initial masses, because entire damn solar masses get radiated away.
Yes, yes, fair point.
I was just wondering, the second part of your talk that is about black holes orbiting other black holes, is this part of the original process you described of them eventually merging, or is this a more stable type of situation?
Good. Yeah, so
It happens in the same amount of time, or they
Good.
stay stable for longer, or what's happening there?
nice. So there are systems also where black holes go around each other and it takes, so in the beginning, sort of, it takes a very long time to get closer and closer and closer. But that part, again, we're just not sensitive to it in our detectors. So that part also happens, right? The black holes have to be closer, but that process is just something that we don't see. With the MRI, indeed, that is something that we do see. We get to see much more of that earlier part, so to say. But I wouldn't necessarily call it more stable. It's just that things evolve on different timescales. So it's a combination of things, like what do we see in our detector and what happens in our universe, right? And in our universe, we have, things slowly evolving and things quickly evolving. What we see in our detectors are typically only the quickly evolving things. But, using, our knowledge and our models, we can then track back about, if we see only these quickly ones, like what is really happening in our universe, right? We can extrapolate.
Well, I was told the microphones are a lie. You can just talk.
Okay. Yeah, thank you for the talk. It was very nice. I have a bit of a naive question, and I wanted to come back to an example that you gave, the bell example. You said that we could, for example, identify the bell just by hearing it. But I would say that it's kind of true if one already saw a bell in his life and that experienced what is metal and these kind of things. So the point is that what do you use as a reference? Because I guess that the wave that you are measuring could have could be explained by different parameters. So you said you just have the spin and the mass of the two objects, but I guess you could have different combinations that give the same final waveform, or not at all.
Good. Yes. So yes. So in this, very nice. So for the bell part, the ringing part, the frequencies are not really determined by the masses and the spins of the two individual black holes, but only by the mass and the spin of the final black hole. Okay. So that's helpful because that helps simplify the problem, so to say. But it is important actually to know the relative masses and spins of the black holes in the beginning, because they tell you sort of the amplitudes of the frequencies. So if you are able to know that, you get a lot of additional information. But that part, again, is very complicated because you have to go through this merger phase, for which currently we don't really have a good analytic handle on. So we have to go through these numerical simulations, and it's trickier. But yes, in some sense, right, the initial masses and spins do come into play, but for the frequencies, it's really only the mass and the spin of the final object that's relevant.
Okay, I'll do a question. You had the slide near the beginning about stellar mass versus intermediate mass. And I think there was a moving of the goalposts there because before the first gravitational wave observation, actually no one expected to see black holes that are dozens of solar masses. And those were called intermediate. And it was a big surprise when they were observed, and astrophysicists had to think, how come they're there? And I don't know what they came up with in the end.
They come up with, well, our astrophysical population models have many parameters, and we can tweak them. But it is true. When the first observation happened, lots of people were surprised. One, that there were black holes and not neutron stars, because most people had expected that there would be neutron stars to see first time, because you sort of have more of them, et cetera, et cetera. Although not everyone, there are quite some papers out there that have actually predictions about black holes being the more dominant ones. And that's in fact actually what we see. But also we were quite lucky that first observation, because that first observation, those black holes are relatively massive. Many of the observations we saw after were lighter, with the exception of the one from last week. That one had a sort of similar parameters again to the first one. Anyhow, yeah, astrophysics, I've learned there are just lots of parameters. Things can still go, not move that much, right? But can still change by an order of magnitude, typically. I don't know if that's reassuring or not, but with the help of gravitational wave astronomy, I think there's more and more data and less wiggle room, right? Things that get more and more constrained. So I think this is good.
Question about your nice animation. What did we see? It was analytical solution or analytical solution plus some actual measurements?
This one,
With the orbits,
yeah. So this is good. So this is a semi-analytic solution.
Okay.
So it uses. So this is actually a system that's kind of interesting. This is something that we cannot just put the complete Einstein equations on the computer and solve, because of these extreme time scales, right? Or well, extreme mass scales, and therefore also extreme time scales and extreme everything. Like this is something you cannot put on the computer, it crashes.
Mm-hmm.
So for this, we actually need analytic tools to solve. So this is a combination of is using black hole perturbation theory at the backbone, and then going to, well, I think this is just first order, but it could be improved. And then you can get something like this. But in even black hole perturbation theory, you can derive the equations analytically, but the solutions you need to solve numerically.
Mm-hmm.
So this again, it's in some sense that's why I call it semi-analytic.
Mm-hmm.
But it's not a complete solution to the Einstein's equation. It's only up to some order in some sense.
Mm-hmm.
Yeah, not everything can be put on a computer.
Have we ever observed two supermassive black holes colliding?
Not yet. No, not yet.
So that would mean two galaxies probably.
Yeah, good. Well, okay, in that sense, yeah, we have seen galaxies merging. There is observational evidence from that. And since most galaxies have a supermassive black hole in them, you could say, well, we have seen black holes colliding. But it's somewhat indirect. With gravitational waves, we will also be able to see it more directly, right? Where you actually get to see two supermassive black holes and get to see the wave from it. But again, we haven't seen it yet with our current detectors because of the frequencies. So the frequencies of these things are, again, millihertz range, much longer wavelengths, and therefore, we don't see that with our current detectors. But we're gonna see it, and it will be super cool. And those things will be, I mean, way more exciting, because for those, right, the signal to noise ratio is a lot larger, right? You can imagine if supermassive black holes collide, the amount of energy released in those events is gonna not just be 3 solar masses, it's gonna be even way, way more. So it will be something much easier to detect in your, with your gravitational wave detector. And therefore, you can do much more precise things. Yeah, I'm quite excited about that too.
When we're talking about precision, of course, classically we know that black holes have no hair, but do you expect any quantum hair in these? Yeah.
No, but the cool thing is we can actually test it, right? So for instance, you can see, well, what if, we don't impose these perfectly absorbing boundary conditions, but say put some small reflection there. It would change the whole story, and it would change the frequencies you would see, for instance, in this ring down, et cetera, et cetera. It's a measurement you can do. There are also things like this, which you call tidal heating. So the gravitational waves are generated and go out, but in principle, it can also be absorbed, right, by the other black hole. Now, if black holes are properly quantized, you could think of that maybe it can only absorb frequencies of a specific, waves of a specific frequency. So it could not absorb any frequency. This could, in principle, also leave an observable imprint. So this is, again, something you could test. Depending on your take on this will be amazing or not so amazing. But to the extent on how well you can constrain things, I don't know. But certainly, if you go to, say, higher order theories of gravity, so right where you not just include the Einstein-Hilbert action, but say R squared, et cetera, those solutions also, or those theories also have black hole-like solutions. They might not be properly full quantum gravity theories, but they could be some effective field theories, valid at some effective field theory correction, right? That you could test for. And some things like, for instance, there have already been quite strong measurements, or an entire classes of theories ruled out, like, for instance, the merger of a neutron star with a black hole. Because from that signal, you can get a constraint on how long it takes for the gravitational wave to propagate and how long for the light it takes to propagate. Both of them are expected to travel at the speed of light. And you can actually measure that and constrain that, and that allows you to do cool tests. So I think some of these things are not super well motivated from the theory side, but we can certainly help constrain things. And then this is being actively pursued as well.
Right. Let's do an enthusiastic thing with the hands.